So a really cool thing about this is you can specify the cut points. So you can say, okay, I think GDP growth is really important in model dependence, so I'm going to make 20 categories for that. I think population isn't very important, so I'm going to only break them into 2 categories. And so you can actually use a lot of your theoretical knowledge, assuming you have theoretical knowledge about what you're testing, to sort of come up with plausible ways to do this and keep as much data as possible. And I don't really know anything about these other matching techniques, but they're out there. They may be useful for you. So quickly, some potential drawbacks to using this technique. As we saw, in this case, we lost 1/3 of our sample size. So obviously, that you may worry that that's going to increase the standard errors, and as you'll see in my example, that can happen. A second critique is that we're already worried about all these modeling decisions and the effect they might have, and we just added about 100 other permutations of how we can pre-process our data before even making those modeling decisions. So we have to decide which technique to use, 1-to-1, k-to-1, all these things we can do that we're just adding more modeling decisions. So the response to the first critique is that the observations you're dropping are in a sense observations that you want to be dropping, because they're ones where the treated and control groups aren't actually comparable, and so you're just asking yourself to make a false inference, which is exactly what happened in the simulation. And there actually are cases where matching can reduce the standard error. Because if you reduce the relationship between the treatment and the covariates, if you pulled up the formula for standard errors of beta estimates in linear regression, you would see that you're actually reducing something that increases your error here. I take it at faith. I'm a software scientist. And so the second one, really the point of matching is, yeah, sure, you're adding all these new modeling decisions. But as we saw before, you're rendering the stuff afterwards not very important. And in general, these choices between different matching techniques just generally don't make a big difference. Remember, we had a job talk in our department, and people were arguing about the the merits of various matching techniques. And one of the elder statesmen of the department raised his hand and says, "Does any of this actually matter?" And the job talk candidate says no. And he goes, "Then why are we arguing about this?" And we all moved on. So let's talk about an actual application of something that I'm interested in, which is again, does being involved in wars increase or decrease leader security in office? So there's been tons written about this, and none of it I think actually is even remotely close to getting the statistics right, sadly. And so one problem that no one has really dealt with is the fact that you need to be in office in order to be involved in a conflict. So if you look at just a simple correlation of how many conflicts you've been in and how long you stay in office, voila, you get a positive coefficient. And people have sort of dealt with this, but I don't think they fully have. That's actually why I started thinking about matching here, because I thought I had a nice way to do this with matching, but then I came up with a better one, which is completely uninteresting for this group. But after fixing this problem, we can do matching, and that actually matters a lot too. Because the other problem is, there's huge problems with non-random selection here. Obviously, some countries are just much more likely to get involved in conflicts than others. Switzerland not going to be getting in many fights. I think in this data set, if you look at even low-level hostility conflicts, I think Saddam Hussein was involved in 38 disputes in his tenure, compared to the modal category is probably 0. So that's a problem. And actually, not only that, but it's a pretty conventional view in political science, particularly in NYU political science, that leaders are basically trying to do whatever they can to stay in office. And so not only is there non-random selection, there's essentially strategic selection where leaders are doing everything they can to stay in office. And so, from that perspective, they're only going to get involved in conflicts that are going to help them stay in office. So if you totally buy that theory, then you'd be amazed to see any result to the contrary, which is what a lot of the past research showed. So this issue, I'm not going to pretend like we can actually solve this with matching. I mean, it's a really hard question. We don't really know the strategic logic behind leaders getting involved in conflicts. It's a really, really hard question. There's tons of measurement error. We don't really know. We don't know what the hell is going on in their heads. So we can't really fix this. But I think that hopefully I'm going to show that matching is much better than just using some regression technique. which is obviously better than doing nothing, or just like doing case studies or something. And so it's also going to use a little customization and tinkering with the matching. So maybe it'll be a teachable moment too. Okay, so the data I'm using. So I've got about, I think there's about 2,000 leaders in this data set. So essentially we have, for every year we have data on how the economy was going there, whether it was a democracy, what kind of democracy, how old they were when they entered office, are they male or female, tons of stuff, disaggregated on the yearly level. So in general, we're using a Cox duration model for this, which I don't know if people are familiar with that, but so our dependent variable is this duration, how long do they stay in office. And so a Cox model is one of the most standard ways to do that. Essentially, you're looking at so again, our treatment here is being whether or not you've been in a conflict in the past, and you're sort of looking at whether or not that increases the hazard rate in the parlance of these duration models of you being kicked out of office. And so obviously I don't have time to go into the details of that. Hopefully people either know about that or can accept my hand waving. And so I'm bringing in this data on these militarized interstate disputes. And so basically all I care about is when they started, when they ended, and again I'm going to restrict my attention here to the worst ones, which I believe means there had to have been 1,000 deaths on both sides of the conflict in order to be coded this way. So these are real wars. So what some people have done in the past is just treat the entire year where you get involved in conflict as the treatment, or use that as the treatment, and then nothing after that, which is just problematic for so many ways I won't even get into it. A slightly better way, this is sort of my what I've done to the data before what I'm going to show you, is to sort of treat all of the post-conflict period as being treated, and then so basically for those who've seen duration models, so if you get into conflict before you get kicked out of office, you treat that as a censored observation, essentially. Which, if you've seen duration models, that should make sense. If you haven't, sorry, don't it's not worth trying to explain. And so hopefully the best thing to do is to run this matching algorithm and hopefully remove these problems of model dependence that we were worried about before. So here is I called this the somewhat naive model. So again, I'm using Zelig. I'm using the Cox proportional hazards model. And I've got all my lovely covariates. And I'm not going to show you the details of everything, but so the estimate you get out of this is that, so being in conflict or post-conflict, you've got this negative coefficient, which means that you're more secure in office afterwards. And as you can see, we've got our almost significant by standards, or standards. So from here it looks like being involved in wars is great. So if you're a leader, don't get involved in wars. Yikes. So I'm sort of doing two stages of matching here. So another thing I'm worried about, actually, if there's anyone here who knows a lot about time series cross-sectional data or matching, this is an issue that I don't think anyone has a solution to. So I'm worried about matching leaders to themselves. So there's a problem where if you have a treated unit where, I don't want to match Saddam Hussein after his first conflict to Saddam Hussein before his first conflict because he can't get kicked out of office then. So I think I want to remove those observations. So this coarse exact matching is a really nice technique to do that. Because I run it once, and then I have all my bins set of the leaders I want to compare. And then I can just go through and check all of those bins and say, okay, am I matching someone to themselves? And if I am, I kick that control observation out. So if I was running this with a propensity score algorithm, I would just have to run it and then check, and then I'll be throwing out treated and control units, and I would be losing more data. So this is sort of the code isn't actually terribly interesting. But essentially, so I'm specifying all the cut points I want. Note that, so these are kind of, you specify it as a list. Hopefully people are aware of lists. Lists are great. And so, I'm essentially saying for this variable, use 0.001, 0.999 as a cut point. For a lot of these variables, I'm just saying, okay, go from the min value to the max value and make 10 cut points. And so at this point, 10 is just a completely arbitrary number, and I'm going to show you why that's really interesting soon. Hopefully really